going to start by just showing you guys a fairly simple example of the Euler phi function. Y'all, in the Euler phi function counts the number of integers less than the input value that are relatively prime to the input value. Now, in the case of phi of 8, this is the phi function, not a q. That's not a very good phi function, is it? But anyway, phi of 8 is equal to 4, it turns out. And I'm going to list the numbers less than or equal to 8 that are relatively prime to 8. Those numbers would be 1, just the odd numbers, right? That's simple enough, right? 3, 5, and 7. And all 4 of these values are coprime to 8. And just an example would be the GCD, greatest common divisor or highest common factor, GCD of 8 and 5 is 1. And the same for the others. I'm not going to write them all down. It's equal to 1. So that's what this Euler phi function does. And again, I could have written down the others too, but I'm just going to write down this one just to illustrate the notation here. Phi at 8 is equal to 4 because there's precisely 4 numbers less than or equal to 8 that are coprime or relatively prime to 8, namely 1, 3, and 5. That adds up to 4. Okay, now so we want to calculate phi of 627. It'd be much harder to do this the way we just did it, right, by listing all that's possible, but it would take some time and very likely a mistake would be made. So we want to calculate phi of 627 from first principles. Now, that's kind of hard to define, but I wouldn't want you to use a formula. There's an Euler formula, a couple of Euler formulas that you can use to calculate this based on the prime factorization. And by the way, 627 has a prime factorization of 3 times 11 times 19. And that takes a little bit of time, okay, to do this, to check. It's clear that it's divisible by 3 because of the sum of the digits are divisible by 3. 11 also, you can check 11 because 7 minus 2 is 5, minus 6 is minus 11, which is divisible by 11, which means it's divisible by 11. There's not one for 19 that I'm aware of, or not a well-known one for 19. But 627 is equal to 3 times 11 times 19, okay? Now, big result along the way here is to observe that 627, the number that we're interested in, is always relatively prime to any integer k that is not a multiple of 3 or 11 or 19, okay? And that's clear, that's crystal clear based on the prime factorization. 327 or 627 is equal to 3 times 11 times 19. So any multiple of any of these numbers would not be relatively prime to 627. It'd be a number, the value would be something greater than 3, I guess. Okay, but anyway, what we're going to do here, we need to subtract all the multiples of these 3 prime numbers from 627. Okay, now let me just give you an example of how we can calculate multiples. It turns out to be very easy, but just like if you had the floor of, let's say, 14 over 3, okay, notice that this is equal to 4, okay? 4 is the greatest integer less than 14 over 3, so this is equal to 4, but notice there are exactly 3 is the first multiple of 3, 6 is the next multiple of 3, 9 is the next multiple of 3, and 12 is the next multiple of 3. All right, so there's 4 of them, but the floor function does that for you, okay? So what we're doing now based on this observation up here is we're going to subtract off all the multiples of 3, all the multiples of 11, and all the multiples of 19. Now you could do that without the floor function, but I just think it's nice to symbolically represent what we're trying to do. You know, since these divide nicely, you know, they're not fractions, you wouldn't necessarily need the floor function, but at least it symbolizes we're trying to find the multiples, okay? This would be all the multiples of 3, all the multiples of 11, all the multiples of 19. Now, one thing, this second part here is kind of tricky and wasn't mentioned right here. This has to do with what they call a principle of exclusion and inclusion. It's covered in a lot of number theory textbooks. But right here, notice that the multiple of 33 would get counted here and here, right? So all multiples of 33 would be getting counted twice from this term and this term, okay? So we have to add, okay, since we were subtracting them off right here, we have to add all the multiples of 33 to correct for our so-called mistake over here. And similarly for the other cases, 3 times 19 is 57, and 11 times 19 is 209, right? So you can see why we have to add, hopefully, this right here is to correct an overcount over here. We subtracted off too many. We subtracted off the multiple of 33 twice. In these two counts, we subtracted multiples of 57 in this count and this count. That explains this, and so on, okay? All right, now, one other thing we have to remember, we're going to have to go ahead and remember we also have to subtract off 627 itself, okay? So I'm going to go ahead and do a subtract 1 right here for that. And this is because, simply because 627, you know, the GCD of a number with itself is just the number, right? Okay, is equal to 627. Okay, so that's why we have to subtract it off again, because it wouldn't be, this number is not relatively prime to itself. It's kind of trivial in some sense. So let's see what the calculation returns for us right here. This would be 627 minus, now what do we have here? 3 goes into this, what, 209 times? 209. Now what about this one? 11, what is this, 627 divided by 11 would be what, 57? Is that right, folks, 57? Or no, what do we need here? What's 627 divided by 11? Is that 59? Or 57, yeah, it has to be 57, the other two, right? 57, so we'll do 57 right here. Is that right? Okay, and then this one would be what, 33? Is that right, folks? 10 times 5, 7, yeah, right. And then this would be 33 right here, okay? Okay, now right here, what do we have going on? 627 divided by 33, would that leave 57 right here? We already done that? No, well, let's see, what is it? 11. We did 3 and 11, so that would be 19. Okay, 19 right here. Here we've done, so this is going to be plus 11. You'll notice the floor function doesn't even come into play here, but the floor function of an integer is an integer. So a lot of you might be wondering about that, but I just think it's good practice to use that symbol. And then right here, plus 3. Plus 3 right here, and then minus 1. All right, what do we get here? So this will be 627 minus whatever this is, 266. 209 plus 57 is 266, plus this number is 299. Okay, not sure what all this is. All right, and then plus 30, 33, and then plus 32 right here. Like that, right, folks? Okay, so this is equal to 659 minus 299. And y'all, did we get luck here? Is that equal to 360? I got 360. Okay. So that means there's 360 numbers. Let me just write this down. Phi, I already forgot what phi looks like. Phi looks like that thing. Okay, so we have phi at 627 is equal to 360. Now, y'all, back up here, I talked about without using a formula from number theory. Let's talk about that number, all right? That particular number is this. You just take the number at 627, okay, and then you multiply it by a succession of fractions. So what are, it's 1 minus 1/3. I've seen this as a homework question in certain number theory books. So this is 1 minus 1/11. And then 1. And the neat thing is you don't have to worry about the powers, even though there's no powers here. If there were powers applied to the primes in the prime factorization, you don't have to worry about them. Okay? But you see, the cool thing about this, oops, that's a 19 right there, right? 19, and then this part is 18 right here. Okay? So y'all, you can see right here that 3, well, let's just write it. This is 627 times 2/3 times 10/11. And I'm trying to show you we should get the same thing if I haven't made mistakes here. 10/11, and then what is this? 18 over 19 right here. Or no, this, God, y'all, this is 1/19. My bad. Let me correct that. That was kind of a mess to begin with. Okay. Okay, that should be 1/19 right there. So this will be 18 over 19 right here. Okay, but we good fortune has come our way, because 3 times 11 times 19, remember, is the prime factorization. So that's kind of handy. So the 67s cancel and you get 2 times 10 times 18, which is 360. Pretty slick, huh? He thought it was very, this guy got excited about that. I mean, God damn, you know. All right, he's looking up at it. 360, but you see they do line up, okay? 360. And that's it. But I kind of like the way you can just do this based on reasoning in the definition of phi, okay?